NeRFs learn from few views, for example 3 views, are often noisy, present inconsistent geometry, or fail to converge. Here we present a generic geometry regularization framework that takes advantage of the differentiable properties of MLP when replacing reloose layers by soft plus layers. In the following, we denote by bold O and bold V the origin and direction of the ray at position X and Y and associated to the camera configuration C. We also denote by D the depth function for a given ray. D tilde corresponds to the same depth function but indexed by pixel position instead. We first propose a first-order depth regularization term where the norm of the gradient of the depth is penalized. We added clipping to avoid penalizing large depth discontinuities. Note that the gradient of d tilde depends on the Jacobian of the camera function C. This regularization is therefore camera dependent. We then propose a second-order regularization based on the normals of the scene. This time, we penalize the norm of the Jacobian of the map of normals. We also propose a camera-independent depth regularization term. See the article to see where this approximation comes from. We now show some visual results when using the last depth regularization term we proposed. As you can see, the proposed method generates a cleaner geometry and a better novel view synthesis, especially for the background of the scene. The depth, visualized at the bottom, is much smoother and do not suffer from floating artifacts. Here is a second example. Note again how that there are far fewer floating artifacts than the previous proposed method. We now extend the proposed regularization framework to surface models. Surface, based on methods like vol-SDF, learn the surface by means of a signed distance function, also called SDF. Using the SDF, the surface is defined implicitly as a set of points of the space such that the SDF at this point is equal to 0. Using this definition, it is possible to compute differential quantities related to surface regularity, such as the curvature. For example, we can use the mean or the Gaussian curvature defined here. Using the curvature, we define a regularization on the strength of the curvature. Once again, we added clipping to avoid penalizing strong curvature. Note how the regularization term is similar to the one proposed in the volumetric case shown previously. The final loss for a regularized version of vol-SDF corresponds simply to the RGB loss, the econol loss, and the proposed curvature loss. We now show visual results for the different values of the parameters of the regularization using the Gaussian curvature.